Okay, let's have a look here. So, firstly, my pen has stopped working. Come on. There we go. Oh, no, it's off again. There we go. Right. So, 1 plus 2i over 1 minus I. Let's rationalize here. So if we multiply above and below by 1 plus I, at the bottom we'll have 2, and on the top we'll have 1 plus I plus 2i minus 2. So that will equal minus 1 plus 3i over 2, which is minus a half plus 3 over 2i. Now, because the coefficients are real, the roots occur in conjugate pairs. So that's the first root, and that's the second root, minus there, 3 over 2i. The sum of the roots is minus 1, and then if you multiply them, that's a quarter plus, no, it's a quarter plus 9 quarters, which is 10 quarters, or 5 over 2. So the following quadratic equation, x squared minus the sum plus 1x plus the product 5 over 2, that will have the required roots. We know one of the roots, and we know the second root is the conjugate. So this will have the required roots. However, it doesn't quite match the form of the question. But the roots do not change for the equation if we simply multiply the equation by 2. So we have the equation 2x squared plus 2x plus 5 equals 0 will have the desired roots. So that's the A and that's the B. The A is 2 and the B is 2. A quick check on my calculator will confirm that. Yep, and that's right. Okay, that's the first part done. The second part now. We want the roots here of Z5. We want to show that the roots add up to minus 1, or in other words, so to show that Z1 plus dot 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 Z4 equals minus 1 is the same as showing that 1 plus Z2, 1 plus Z2, hang on, I'll write that a bit nearer. Basically, we're required to prove that 1 plus Z1 plus Z2 plus Z3 plus Z4 equals 0. Or, in other words, that if you take the polar form, you could write it like this. That we have to show that all the roots add up to 0. So the equation Z5 is equal to 1, and 1 in general polar form is 2n pi plus I sine 2n pi. So that means Z would equal, you take the fifth root here, and De Morrison said that the power multiplies the angle, so that gets multiplied by a fifth. So that's it. If you index this as n, then Z0 will be 1, and Z1 will be this one here, and Z2 will be this, and Z3 will be this, and Z4 will be this. So now we're required to prove that the sum of Zn is equal to 0, where n is 0 to 4. So what you might not know is that there's another version of the Morrison Theorem which says this is the same thing as e to the power of I times 2n pi over 5 from 0 to 4. So we're required to prove now that this adds up to 0. Now, that's a geometric sum, this is geometric, where the first term, a, is 1, because if n is 0, this is 1. And then each time, you're multiplying by e 2 pi over 5. Okay, so if we use the geometric formula now, let's have a look at that. So I'll just clear this off. So now, since it's a bit confusing, there's 5 terms, so this is actually S5. And it's a times 1 minus or power n, which is 5 over 1 minus or. The a is 1, so it's just going to be 1 minus e power, what was it? 2. Oh, I have to go back in time. Should have written the last piece down. Yeah, okay. I think actually, I'm glad I went back because I think I forgot to mention the I. Where's my, there's an I here as well. I forgot about that I. So it's 2/5 pi I. Okay. 2/5 pi I. So S5 is 1 minus e 2/5 pi I power 5 over 1 minus e 2/5 pi I. Okay, so that's equal to 1 minus e minus 2 pi I over 1 minus e 2/5 pi I, which is equal to 1 minus bracket cos minus, but cos is even, so we don't care about the minus, plus I sine, and sine is odd, so the minus comes out, all over 1 minus e 2/5 pi I. Sine of 0 is, sine of 2 pi is 0, and cos of 2 pi is 1. 1 minus 1 is 0, and the denominator is not 0. So we've proven that the sum of the 5 roots is 0, or equivalently that Z1 to Z4 is minus 1, or equivalently that is minus 1. Okay. Prove that that transformation is a real number. Okay, so that's a half times x plus iy plus the conjugate, which is x minus iy, minus I over 2, x plus iy minus x plus iy. The x's cancel there, and the y's cancel there. So that's 2x over 2 minus I over 2 times 2iy. 2 is cancel. So that's x minus I squared y, which is x plus y, which is obviously a real number. Indicate on the Argand diagram the set modulus is set less than or equal to 1, and find the length of its image under the above transformation. Interesting. The transformation. Interesting. Okay. So we have, here it is. This is on the Argand diagram. 1 I, and it's everything here. That's the set. So for example, here 1 plus 0i would just become 1. 0 plus I would just become 1. Minus 1 plus 0i would just become minus 1. And then 0 minus I would just become minus 1. And then like they're the extremes. So everything else is going to fall within that. So the set is just going to get squished down into this here. This line here. I mean, I don't think I can get pushed outside of it. Like this point here, for example, is 1 over root 2 plus 1 over root 2i. That's going to go to 2 over root 2, which is root 2. Oh, that does get pushed outside, doesn't it? So that gets pushed out to here. And then on the other side, it'll get pushed out to here. So minus root 2 to root 2. That's interesting. Yeah. So the answer would be from minus root 2 to 2. So that's 2 root 2. Interesting, interesting, interesting. So the extremes happen here and here. Well, that comes from calculus. When can you maximize? And it's often at 45 degrees. I wonder if they expect you to know that piece of calculus knowledge here, or if there's some other way to do it. Because if you think about it like this, z is cos theta plus I sine theta, and the image, the mapped z, becomes cos theta plus sine theta. So what's the maximum here? The maximum occurs when theta is 45 degrees. So that's 1 over root 2 plus 1 over root 2, which is 2 over root 2, which is root 2. So, yeah, interesting. Interesting. So this is a very tough complex number question. This is one of these questions where I didn't get it the first time because I got stuck here. And I'm not sure if my method is what they used back in 1980, whatever. But it's the only one I could think of here that didn't require the use of a calculator, something you probably couldn't use in the early 80s. So there you go. Tough question.